All right, everybody, welcome back. So now that we've met the basics of logarithms, we'd like to meet a little bit more basics so that we can kind of go forward to see what's good about these logarithms and how might we use them in a sort of nice algebraic context of solving equations. So the first two of these basic properties here come directly to us from basic properties that we knew of exponential functions. The first one here says log base b of 1 equals to 0. And this corresponds directly with the exponential function fact that b to the 0 equals to 1. This is for any eligible base b, right? Something bigger than 0, but not equal to 1. Okay, and similarly, we have log base b of b equals to 1. Well, this corresponds directly to the exponential function fact that b to the 1 equals to b. Okay, and so these two we get kind of for free from exponential functions and the definition of logarithm. These next two are pretty useful, and they go together hand in hand to help us get some kind of nice algebraic way of solving equations that involve either exponential functions or logarithmic functions. So this first one says log base b of b to the x equals to x. Well, let's try to unpack this. Is there a corresponding fact about exponential functions that this is trying to tell us about? Well, if we follow our nose, we'll read this off. It says that b to the x equals to b to the x. Oh, that's certainly true, right? B to the x equals b to the x. It almost feels like we're saying nothing, but we are saying something, I promise. Namely, that log base b of b to the x equals to x. Okay. The next one of these facts says b to the log base b of x equals to x. Well, this one might take a little bit of unpacking. Why don't we take this? Here we have log base b of x. This is just supposed to be one number, so let's call it y, okay? So then if y equals to log base b of x, then we know that b to the y equals to x. Oh, okay, so exactly, that's like saying exactly this here, that namely b to the y equals to x. Very nice. So this one, again, is almost saying basically nothing of like nothing too complicated once you kind of unpack the definition. So look at these two together, though, 3 and 4. These are compositions of functions on the left of each one of these. The first one is the composition where b to the x is the inside function, and then log base b is the outside function. And look at the effect. If you start with x and then first exponentiate it, base b, that is, first do b to the x, and then follow that by log base b of b to the x, what you get is just x back. So you undo the exponentiation by taking the logarithm. And going the other way, taking the composition of first doing log base b of x, and then exponentiating that base b, doing b to the log base b of x, that also has the effect of undoing the logarithm and leaving you just with x. So together, these two properties tell us that log base b of x and b to the x are inverse functions of one another. So in particular, I think we've seen graphically before that b to the x is 1 to 1. It will also be the case that log base b is a 1 to 1 function. So let's do this example here where we just invoke a few of these properties. So log base 9 of 1 should be 0 because 9 to the 0 equals 1. That corresponds to this property 1 here. Log base 11 of 11 equals to 1 because, again, 11 to the 1 equals 11. That corresponds to this property 2 here. Log base 7 of 7 to the square root of x. Well, this will be the square root of x, corresponding to property 3 here. The idea is that exponentiation and log of the same base will undo each other and leave you just with the guy that's up here in the exponent. And The last one here says 4 to the log base 4 of 5. This corresponds to the last property up here, which says that we should just be left with 5. Okay, and as we've stated from above in examples 3 and 4, that the functions y equals b to the x and y equals log base b of x are inverses of each other. In particular, their domain and range are interchanged. And we can graph them by taking the function y equals b to the x and reflecting it over the line y equals to x. That's that interchange of domain and range. So let's plot a few points here too, just to be sure that that is what's going on. So if x is 1, log base 2 of 1 equals to 0. So 1 comma 0 is on the graph of log base 2 of x. Okay, if x is 2, log base 2 of 2 is 1, since 2 to the 1 is 1, or sorry, since 2 to the 1 is 2. So the point 2 comma 1 is on the graph of y equals log base 2 of x. Okay, when x is 4, log base 2 of 4 is 2, since 2 squared is 4. So the point 4 comma 2 is on the graph of y equals log base 2 of x. And last here we have is when x is 8, log base 2 of 8 equals to 3, since 2 cubed is 8. Okay, and that tells us then that the point 8 comma 3 is on the graph of y equals to log base 2 of x. And here they've already given us the graph of y equals 2 to the x. So you can see now the symmetry that the two graphs have along the line y equals x. Notice the horizontal asymptote of y equals 0 that comes about from the graph of, y equals 2 to the x. That one gets flipped across the line y equals x and becomes a vertical asymptote at the line x equals 0, the y-axis, for the logarithm graph. So logarithm graphs have a vertical asymptote as opposed to the horizontal one that exponential graphs have. And notice too, since the range of the exponential function is all the positive numbers, the domain of the logarithmic function is going to be all the positive numbers. In particular, 0 is not included. Okay, and the domain of the original exponential function is all real numbers, because you can exponentiate any real number so long as your base is a legitimate one. And that tells us then that for the logarithmic graph, the range will be all real numbers. So then those points are all summarized here. So we have that every logarithmic function for base b bigger than 0 and not equal to 1, the domain is 0 to infinity. The range is all real numbers. There is a vertical asymptote at x equals to 0. And the graph will always pass through the 2 points 1 comma 0 and b comma 1. Notice we had that here, 1 comma 0 and base comma 1, where the base was 2 in this example. Okay, and so one last thing to note here that we didn't get to see from the above example is that when b is greater than 1, log base b of x is an increasing logarithmic function. So that 2 to the x is one of those. We've seen that here. And then when b is between 0 and 1, log base b of x is a decreasing logarithmic function. And so I don't think we'll see an example of one of those here today, but that's all right. So the last two examples here ask us to just draw a rough sketch of a couple of logarithmic functions and find their domain. So they give us here y equals to log base 5 of x. Well, there's nothing different going on here. It's just that we are given a specific base of b equals to 5. So this one's domain should be the x that are greater than 0, or rather the interval from 0 to infinity, not including 0. And we know that just to do a rough sketch, we can put these 2 points down, 1 comma 0 and 5 comma 1, and then just fill in accordingly with this vertical asymptote at x equals 0. Okay, and then for this very last example in this section, ask us to sketch the graph of y equals to log base 3 of x plus 4. That's x plus 4 is inside the parentheses there. So notice this one has been given a shift to the left by 4, a horizontal shift to the left by 4. So in particular, that will move where that vertical asymptote goes. It used to be at x equals 0. Now it's going to shift back to x equals to minus 4. And we need that whenever we take a logarithm, the thing that we take the logarithm of needs to be greater than 0, right? Followed by this fact that domain of log base b of x is got to be 0 to infinity. So that means that x plus 4 needs to be greater than 0. So if we solve this inequality, we get that x is greater than minus 4. And again, that corresponds to how we had shifted our vertical asymptote backwards, or back to the left, by 4 units. And so let's see, what are a couple of points that are on this one? Well, let's see. If we put in x equals -3, we have -3 plus 4 is 1, and log base 3 of 1 is 0. So we can write here that -3 comma 0 is on that graph. And if we put in x equals -1, we get -1 plus 4 is 3. And log base 3 of 3 is 1. So -1 comma 1 is on that graph. And so I just put those 2 points along with the asymptote and just kind of filled in the rest by just kind of winging it. OK, so this is a new kind of rule, a domain rule to put in your sort of domain toolbox. So we had before that whenever you take the square root of a number, the number that you take the square root of needs to be greater than or equal to 0. And now we have a new rule that whenever you take a logarithm, the number that you take a logarithm of needs to be strictly greater than 0. So it cannot equal it. And our one other domain rule that we still have floating around is that you can never divide by 0, right? I think that one's becoming more and more canon as we go. So so we'll see you next time where we'll explore some more properties of logarithms and maybe eventually get around to solving some equations using logarithms. We'll see you then.